That's a good segue. So, Mark, you're a specialist in this area, right? So you've got your marching orders now from Leslie, and how you're going to go up there after your fundraising completed, and how you're going to deal with the environment. So we had an introduction from you earlier, but
that was actually very good leading.
This is your slide now, right?
This is mine. This is my steps. Okay, developing concepts for asteroid resource projects. This is a follow-on in addition to the talk that I gave 2.5 years ago at the first Off-Earth Mining Forum. Quickly, the DSI team. Quickly, the DSI vision we talked about this morning. We want to supply space resources for enabling human settlement of the solar system. Target lists, where to go to. Asteroid target lists, regolith models, and resource assessment are three areas that have been exercising my brain over the last 1.5 years or so. Why? Well, target selection will drive mission timeline, mining rate, and power. Regolith modelling drives anchoring and miner and processor design, and resource definition is needed to provide assurance of resource availability to the financiers. I'm jumping around a bit here, and I'll apologise for that, but it'll all come together at the end, I think. For how many people in the mining industry here? Good. The resources of near-Earth space, quoting Professor John Lewis's book by that same name from about 30 years ago. Near-Earth asteroids contain regolith, sand gravel, reduced metal, magnetite, water in clays and salts, and possibly free water as ice, gases, CO2, CH4 and others, and a fascinating mix of gases that they found emanating from comet 67P Churyumov-Gerasimenko. Kerogen, asphalt, long chain, complex carbon, natural plastics sort of stuff. Platinum group metals and silicates, olivine, pyroxene, phyllosilicates and feldspaths. And it's pretty obvious that these can produce products that can be of use in space. Raw silicate can be used for ballast and for radiation shielding, and for heat shield, making heat shield for re-entry vehicles. Water and volatiles can be used as feedstock for or directly as propellant. Nickel iron metal for use in construction, making sheet and beams. Reflector sheeting, reflectors, antennae, large antennae, unlimited size. PGMs for export to Earth, and I'll talk about that a little bit later. It got a lot of press early on the piece of discussing asteroids, and it's really only ever going to be a byproduct, not a major product. And I'll show you the mathematics of that later. Silicon for making PV solar arrays in space. Space sources of commodities will displace Earth materials due to the Earth launch cost. And the present Earth launch cost to low Earth orbit is of the order of $4,000 to $13,000 per kilogram. The present cost to launch something to geostationary orbit is $17,000 to $33,000. Now we, within DSI, have to try and make a prediction of what that's going to be in 2020, 2025, and we've quizzed people like SpaceX, and our reading is that by sometime between 20 and 2025, the launch cost to LEO has to be assumed to be down to about $1,000 per kilogram, and the launch cost to GEO has to be down to something like $4,000 per kilogram. And we have to beat that price point. We have to be able to bring material back from asteroids, turn that into usable commodity at less than that price, otherwise we haven't got a market. So the value of asteroid regolith at the moment, typical asteroids, an S-class asteroid, a stony iron asteroid, a stony asteroid will contain something like 20% nickel iron and 50 ppm platinum group metals. Or if it's a C-class asteroid, it will contain something like 10% hematite and better than 10% water and other volatiles. How do we know? From the meteorite collections in museums. These numbers give asteroid regolith, asteroid soil, recovered asteroid soil, a value presently better than $1 million per tonne for its contained water and metal delivered to low Earth orbit, and presently better than $4 million per tonne if delivered to GEO or higher. But only $4,000 per tonne for its platinum group metal content returned to Earth. That's why platinum group metals are not, repeat, not the story for asteroid mining. Just a little aside here, and I thought it's a lovely, isn't that picture of Matilda a beautiful picture? But $1 million per tonne ore is very valuable ore. Mining project concept development in terrestrial circumstances follows these sort of steps. In terrestrial mine planning, well, I'm going to get to the steps, but it requires choosing between competing mining methods and competing metallurgical extraction concepts to produce, to design, to develop, to envisage a project which provides the desired production rate of whatever your desired component is, which minimises the capex and the opex, the capital expenditure and operation expenditure, and minimises the payback time, and minimises the project risk, so as to maximise the expectation net present value. That's what we've got to do for space mining as well. If we don't do that, we don't have a project that flies. So to repeat, an asteroid mining project economics study is driven by capex, payback time and net present value. Mission duration and mass returned are key inputs. Specific mass throughput of the miner is a key input. See that profiler that Leslie showed chewing through the bitumen? I had exactly that same model chewing past my house 2 weeks ago. And I went out and asked the guys, how many tonnes per hour does it do? None of them knew. So I get out my smartphone and got the stopwatch on and clicked it, and it was running at that stage 100 tonnes an hour. They didn't know. But that's the sort of thing that you look at and you say, I can take one of those things and modify it for asteroids. Specific mass throughput of the miner. Miner mass and launch cost. Delta V for return from the asteroid to Earth orbit capture. Power and propulsion systems parameters. And value per kilogram delivered to LEO, GEO, or higher, highly elliptical Earth orbit. Like Earth Moon L1 or a highly elliptical orbit for Mars departure or something like that. Project choices. We will need to choose our targets and our mission types. We will need to choose our markets. What and where? Is it going to be water? Is it going to be storable propellants? Is it going to be metal? And is it going to be for delivery into LEO or GEO or HEO? Propulsion technology, anchoring technology, mining technology, beneficiation processing. We've actually performed a first pass concepts development paper scoped to return 1,000 tonnes of water to high Earth orbit in a period of a decade. And we've got another document which I forgot to bring down, which we're working on at the moment, which is a concepts development document for asteroid mining in general. But you've got to be very forensic. You've got to pick the different parts of the story apart and study each of them very carefully. The value proposition, just to backtrack here, is the near-Earth asteroids are numerous. There's something like 13,000 now known. So something between 15% and 17% of them are energetically closer than the Moon. More than 50% of them are prospective for water and or nickel iron. They are potentially very valuable ore, and potentially the extraction processes that you need, water by heating, metals by magnetic separation, are intrinsically simple separation processes. Okay, and then you can go on to getting everything out of the pig except the squeal when you do further and further processing of this stuff to get everything out. So design driver, maximise expectation net present value. Minimise capex, do it robotically, 1 or 2 launches. Minimise project risk, implies simplest possible collection, processing and propulsion systems. Keep it simple, stupid. Maximise return payload. The return leg is the most important segment to optimise, and thus the return delta V must be minimised. You've got to pick a target that gives you low delta V out and minimal delta V back to try and optimise your project. You've got to try and minimise the mission duration because time value of money. And also there is a cost, a deep space tracking network cost, operational cost in the mission duration. Synodic constraints means that most of these things are only intermittently accessible. We have to take all that into account, and that's a project scheduling issue, isn't it? The remote space miner must achieve anchoring onto a microgravity body, it must achieve collection and comminution, must achieve ground control even in micro G. If you're burrowing in and the ground falls in on you, it's a serious nuisance. Containment of product cuttings, transport of cuttings to processor, separation and storage of the project. We've reviewed multiple mining methods and have developed a humongous conceptual process flow sheet, the first simple part of which is applicable at Asteroid, and the tail end of the later part being for an in-orbit processor for delivering to expanding orbital economy. Concepts that people outside the mining industry need to learn about are ore, grade, ore body model, mineral resource, ore reserve, mining and processing methods, concept development, scoping, pre-feasibility and bankable feasibility studies, project valuation and so on. I keep saying to people we need to learn these terms. In the terrestrial mining project pathway, this is the flow sheet that a company board will have in its mind when it sets its chief geologist or its exploration manager to work. Do some desktop studies. Figure out what commodity we're going to go for and where. You look at the open literature, university PhD theses, School of Mines papers, geological survey papers, and you end up, well, we're going to go for copper in Chile, or we're going to go for coal in Kalimantan, we're going to go for coal in the Bowen Basin, or the Sydney Basin, we're going to go for lead zinc out around Broken Hill, or we're going to go, you pick your commodity and your general area, then you begin to zero in, you target down. By theory, and by looking at the papers, and ultimately by field work, you end up with a mineralisation, a body of mineralisation. Is it mineable? You don't know yet. You've got to get some quantitative figures, so you've got to quantify. What's the inferred mineral resource within this body of mineralisation? And then the modifying factors are how costly will it be to mine? How costly will it be to process? And when those go together, that gives you your ore reserve. So I've been given a bit of a warning. What's that, 2 minutes? 5, okay. But this sort of progression is exactly the sort of progression that we have to follow through in fleshing out asteroid mining issues, and indeed moon mining. This sort of progression. If you don't use this sort of progression, why do you expect anybody to believe you? Defining our asteroid projects. I think I've said most of that before. Delivery to where is interesting. Mining methods, surface, reclaim or underground. Beneficiation and processing, how far do you take it? How far at asteroid and how far at a Earth orbiting processor. We've been thinking through selection rules and figures of merit for shortlisting our targets. I've been reviewing and developing probabilistic resources assessment methods to take targets and say, with the general information we have from the literature, this is the sort of probable resource recoverable. You end up with a sieved set of target shortlists. I'm just going to skip through these. So, we will be developing a bankable feasibility study. Desktop conceptual study is sort of where we're at the moment. I have to bring the desktop study, concept study to completion over the next month and a half, 2 months, something like that. That leads on naturally to a scoping study. That leads on to pre-feasibility study and final definitive and banking feasibility study. So there's lots, there's something like, if you look at those histograms there's something like 9,000, 10,000 near-Earth asteroids above about 30 metres diameter. We think that the good mining targets are those above about 100 metres diameter. Substantial number of those near-Earth asteroids are more accessible than the Moon, and a substantial number are in fact potentially hazardous asteroids too. So we diminish the risk of Earth impact as we mine these things. NASA Trajectory Browser is a lovely tool that I encourage people to have a bit of a look at if they want to have a bit of excitement. It gives you an interesting array of potential targets and their trajectories. And here's a refined target list, and here's our mineralogy and analogues with meteorites. Ore body concept, there's basically two major headings of ore body concepts. One is the regolith draped rubble pile, and the other is the crypto-cometary body. And the classic for the regolith draped rubble pile turns out to be Itokawa, which has got a density of about 2 grams per cc. That object is about 500 metres long. Lots of porosity in it, obviously, because the density of the minerals is about 3.5, and here it is, its bulk density is 2, so obviously a very porous body. And the crypto-cometary asteroids are about 50% water by mass and highly porous, and they're supposed to be quite low tensile strength. But the classic of that is, of course, the information coming in right now and over the last year from Churyumov Gerasimenko. How's that? Porosity greater than 70%, very gassy, it's giving out lots of water, lots of gases. We believe that there is a hardened layer below soft layer, because otherwise Philae wouldn't have bounced. That was foretold in comet crust models from back about the late 70s, mid 80s. We have to, I'm jumping around here, but I haven't ordered these slides properly, but obviously I have to get to the point of showing you how we get an inferred mineral resource. Estimation of mineral resources has to be done by mining companies and exploration companies when they front up seeking to raise money on the Australian Stock Exchange or the Canadian Stock Exchange. And you know, there's a thing called the JORC code, the Joint Ore Reserves Committee of the Stock Exchange and OEMF. And the Canadians use National Instrument 43101 to substantiate their claims of what they think they've found. And if you don't work through these things, or something that can be seen to be parallel to them, then, you know, the stock exchange won't believe you. We can't do a JORC drill out of an object that's 200 million and 100 million and varying day by day, kilometres away. So what to do? And I stumbled across this US oil and gas industry guidelines for application of the petroleum resources management system, where it walked me through a probabilistic method. And I'd heard from others that the BHP Billiton uses a probabilistic resource range analysis for categorising, ranking investment in greenfield projects and projects with sparse data, and this is sort of similar. It's a stochastic or a probabilistic approach rather than a deterministic one based on hundreds of drill hole data. It uses probability tree analysis, and I worked through the methodology and got a distribution like that for a hypothetical dark asteroid. And that says close to 100% likelihood of getting a little bit of water and 50% likelihood of getting, you know, 600 kilotons of water for a certain range of situations. But interestingly, the shape of the curve, when translated across to what the oil industry says is a good shape, the shape of that cumulative probability is very similar to the green one there, which is called a discovery. We've got a totally different situation in space where most, I repeat, most, more than 50% of the targets, even without any spectroscopic information, even without any albedo information, are prospective. More than 50% likely to be resource bodies. Whereas on Earth, at the same sort of desktop study level, you'd be likely to have a 1 in 1,000. You'd be likely to have 1 in 1,000. So the takeaway messages are these. We've got a high and increasing discovery rate of near-Earth asteroids. Most contain easily extractable, potentially valuable products. Access to the NEA resources is technically within reach. No more difficult than flying out to putting a geostationary satellite in orbit, frankly. Really, truly. The delta V is the same for some of these things. Terrestrial minerals industry concepts are important in mission definition. I've told you some of the things you've got to think about. It's important to put asteroidal resource estimation on a sound footing, which I believe I've done. This removes a major mission uncertainty. We see a self-supporting way forward to profitable asteroid exploitation, and we believe the near-Earth asteroids will be major resource opportunities of the 21st century. And here's our pathway for accessing these resources: consulting and study contracts, spacecraft construction contracts, rendezvous missions, sample return, then bulk mass return. And the virtuous circle is thus delivered where we have special insights and technologies, identify and access superlative ore bodies, first in market, gives proprietary knowledge, which gives you even further insights, which reduces the risk and cost versus any later entrant, which gives you overwhelming, ongoing, technical and economic advantage.
Thank you, Mark. We don't have a lot of time for questions.
Because I took it all up.
You took it all up, but you know this man is, you've managed to find literally pie in the sky.
I have.
You have. Fantastic. Thank you. Thanks, Mark.